Yeah.
It's time to get started. First item of the agenda is to introduce this fine gentleman who is just off camera, so that anyone who is looking back on this has no idea who I'm talking about. Okay,
I'm
yeah,
Hunter, I'm the TA. Come to me if you ever need any help with the class or whatever. I'm ideally just as good at answering questions as him, but sometimes that's not gonna be true. But I'll do my best. If you ever need help, just like come to my office hours. I'll be there. Did you get my office hours yesterday? Okay.
so
I'll pretty much be there from like 9 until 1 almost every school day. And also if you need to like DM me on Discord, I'll usually respond there real quick, or message me on Canvas or email me, just whatever. If you can't get a hold of him, and you still need some help, you can ask me and I'll do my best. That's
Excellent.
pretty much it.
any questions for Hunter? All right, he deserves a massive round of applause. Even though he hasn't done anything for you yet, he's amazing.
Just like.
And I'm not gonna hurt him.
I take that.
The louder the applause, the better grades you will get from him. Okay, I already hate this room because it's really hard to do everything that I feel like I need to and continue to make eye contact with everyone. So we're just going to figure it out as we go. Does anyone have any questions, or was anyone not here yesterday? I think that's the big one. Aside from Brian, we know where you belong. We know what group you belong in. Everyone else is here, knows who their group is, and are you sitting with your group?
Yes.
Awesome. So first of all, we will have some, what do I want to call it? Agenda items, I guess, for what to expect over the weekend, because this is the last meeting of the week. We don't meet tomorrow. I will be revealing the easiest assignment you have ever done at some point later this afternoon. It should take almost no time at all. I just need 2 important pieces of information from you. I believe I'm going to end up needing your Discord username and your GitHub username. If you do not have a GitHub account, you will need to create a GitHub account and then deliver that information. Just those 2 pieces of information will give Hunter enough information to be able to create the Discords, post the invite links for the Discords. I actually don't know if we need your Discord username. And get the GitHubs set up and get you all invited and the appropriate permissions set to those GitHubs for your collaboration. I'd like to get that done by the end of the weekend so that starting at the very beginning of next week, you're able to start working on Sprint 1. Remember that the goal on Monday is also to have a discussion about the first chapter of debugging themes. So instead of working on crazy amounts of coding over the weekend, your task is to read the first chapter of debugging themes. I will come to class on Monday prepared with a list of discussion questions. I think I mentioned this on the first day. If I didn't, I'm going to reiterate it now. I hate cold calling. I'm not going to cold call on you, but I would appreciate if you come as prepared as possible to have a real discussion about this material. You'll be able to contribute to the best of your ability, given that you've read the material. So it's mostly going to be a discussion about what is talked about. It's not like contribute to what was already said in the book. It will be more of a add to this material with your own life experience, your own thoughts, your own ideas, and you'll be able to base that on what was said in the book, and your arguments will be the strongest if you can tie that all together. Any questions about expectations over the weekend in preparation for the start of next week? Awesome. I think part of that assignment will probably be to include your team names so that we can group you together, and that is when I will learn of all of the team names that you have created. So if you have not created and finalized a team name yet, you should do this by the time that you get out of here today. By the time you leave your group, you should have agreed on that. It's probably also good if you exchange some kind of contact information outside of Discord. That way, you have multiple ways of getting a hold of each other. It will reasonably be important to set the expectations of kinds of communication, what is appropriate communication for. Any other administrative questions before we get back into what we were talking about yesterday? Yeah,
I forget, did you have a link to the book on the campus somewhere?
it is in the syllabus, which is actually visible now. I doubled back and checked, and all of the work that I did hadn't been saved. So it did it all and then didn't actually publish the syllabus. It should be live. Someone should go into Canvas and verify that you can see it yourself before the end of class. That way, you can all see the syllabus. Yeah, the link is there. If you just Google debugging teams, the name of the book, it should be the first link that you get as well, but the actual link is in the syllabus.
I did have to find it online because I checked last night because I wanted to crack open early.
Yes, very, very nice. I
It is
apologize
for
for
free.
that.
It is for free. It's just teamdebugging.com.
Yeah,
And it's that website and you can get a free PDF and just read it online.
Yeah.
You don't have to worry about buying it.
Exactly. Yeah, that link, the link that's in the syllabus is directly to that site, which gives you the PDF. You can download the PDF, read it directly in a browser. Doesn't matter, it is free. No one should spend a single penny on this class. Aside from the tuition, of course.
One more thing, yesterday you showed us kind of a breakdown of what Sprint One's gonna look like.
Yes,
Is that something that's posted now or is that coming?
not yet. I don't think we should be worrying about it because I don't want people to get too far underway before we start talking about the actual process that you should be going about. In order to do it, I just wanted to give you an idea of kind of the sprint size, what to expect. This is going to be a reasonable amount of work. My goal right now is to say, once you get the all green, you're gonna need all of that time to make sure that everything is done and working together, because it's one thing to be doing this yourself, or you can procrastinate it and do it the night before it's due. It's the other when you actually have to test things that your fellow group mates are working on, and something's gonna go wrong during that phase of your development. And there's gonna need to be some back and forth. You're gonna need to fix some aspects of your code. They're gonna need to fix some aspects of their code. You need to come back and test it again and make sure that it's all working together. It's a much more involved and longer process than you might be used to in the programs that you've written for your other classes. So we'll talk much more about that as we get to the green light, but I anticipate the green light to be about Monday of next week. And we're gonna start learning a little bit of GitHub stuff then, so that you know exactly how to contribute to the larger project. By then you will have GitHubs. Other questions? This is all great so far. Good to go? All right, let's do it. We ended yesterday's class talking about how to efficiently develop software. So when we have a larger project, we need to start thinking about how do we divide it into pieces? How do we work on those individual pieces, and what's left to do when we want to fit those pieces back together? We'll talk a lot more about this as we talk about, a lot more detail, the different kinds of development principles that have historically existed and what is used today. One other important part of this is going to be verifying what you have written. How do you know for sure? How do you prove that what you have written works? We'll have a chapter or a unit on this as well, but the answer is, regardless of how many tests you write, you can never be 100% sure. Yet, there is a way to be 100% sure that your program works for all inputs. We can read the slide or guess, what do we think that is? What is the way to 100% guarantee that your program works for all inputs?
Try to break it.
You'll never be able to test all possible inputs.
Limit the amount of inputs it can take.
That sounds like a recipe to produce something that is not particularly useful. What if you want to then expand on that to incorporate more and more, and there are going to be an infinite possible inputs? Then you have to segregate your program into so many different pieces that there's still an infinite number of pieces of finite size to create the infinite number of, there's an infinity somewhere in that. It's a good idea. What no computer scientist wants to read or think exists. Formal mathematical proof. You'll need to find a way to go line by line in your program and turn this into kind of a discrete math type of proof. For all possible ways that you can end this line, you begin the next line in such a way that if this line is correct, then this line is correct. And you end up with a big logical web of discrete type proof. We'll talk about what that looks like. We're not gonna do a ton of it in here, but you should at least know what that looks like and how much work that entails when it's worth trying to do this and when it's a huge waste of time, because it is very time consuming and very expensive in terms of man hours and just the raw amount of intelligence that you need to do to go through this process. But formal verification is the only way to know for sure your program works for an infinite number of inputs. So you will need to go back to math proof from the screen. I'll give you a very brief introduction to this concept for now. So here is a very simple program. We are going to add an object into, this looks like something like a linked list. Could we say or prove that this program works for all inputs? First of all, what do we mean by works? Works is kind of a vague word here. We need some kind of further description or logical understanding of. We need some question to actually be able to answer. Yeah.
A program that runs and does not produce unpredictable or unexpected output.
Okay, that's a nice general definition. For this exact problem, how would we know that this is correct or that it works? I completely agree that that's a good definition in general.
If the size keeps growing.
So at the end of this, the size should be one larger than it was when we started. Sure. Is that the only thing that we need to verify?
The correct object added.
Yeah, that the object is at some associated index in our linked list. So we can ask lots of questions about this. So this person here says, can you verify my program? This is too vague. We need to be able to further specify what property are we interested in verifying, because formal verification will only answer one of these at a time. So kinds of questions that you could answer about this: will the program crash? That's a binary yes or no. Does there exist some input for which this program will crash? That's a yes or no question that you can answer. The answer will not be both yes and no. It will not be neither yes nor no. It'll either be yes or no. Does it compute the correct result? This is obviously not for a linked list operation, but if there's some kind of arithmetic associated with the program, if there's an anticipated output to the program, is the output always the correct result? You could ask other questions. Does it leak private information? Kind of important from a security perspective. Even if your program is 100% correct in every other regard, it doesn't crash, it does what it's supposed to do, there may be a security vulnerability in it. You could verify, is there a security vulnerability, a particular kind of security vulnerability in the program? How long does it take to run? You could figure out a mathematical order to associate with your program. You can formally verify the runtime of a program. How much power does it consume? You could ask on a particular setup, exactly how many kilowatt hours is it going to consume when this is tasked? If there's a very specific application, we're now using software in a self-driving car. Will this program ever turn off automated cruise control? Something that very specific question that you can ask that is a binary yes or no answer. So all of these questions could be answered by formal verification. That might be really difficult to answer otherwise because there are an infinite number of possible inputs and or an infinite number of possible outputs. There's just no way we can write tests for all of that. Okay, back to the example. I want to be sure that no element is lost in the list. If I insert an element, is that element really there? Is it in the list? Can we formally verify that? Does anyone have any idea of how you might logically verify that for any possible element and any possible size of the list?
But you not just wanna like root through the list and like check it against the one you just made, maybe save an extra copy as you like to.
Potentially. You could think about it in terms of writing a program to verify that.
So I would just write another function that checks it after you make it. Although we kind of.
What size of a list are you gonna start with?
2.
How many possible sizes of a list are there? Is there any guarantee that the code that you write works for a differently sized list? How could you prove that?
I hate to bring it up, but inductive proof comes
Yes.
to mind.
Yep, would be a proof by induction. The reason that these are brought up in discrete is because they're actually relevant to formal verification. The entire reason that it's part of the computer science curriculum, really, there's more than that, it'll come up in compilers as well. Your future selves will think, as you take compilers from me, those of you who do. But inductive proof is very common in computer science wherever you have something that is a sequence like this, where you have a list of a particular size. You have a list of size n here, and by the end, you have a list of size n plus 1. You make the associated assumption of starting with a list of size n. This is not something that you can write code for. You can't say, instantiate me a list of size n. There are an infinite number of lists. What does the CPU do? It can't do that. So you have to fall back on mathematical theory to be able to say, okay, well, we have rules of induction. How could we show the associated size grows by 1? And according to this exact sequence of instructions, the last element in the list is going to be the new element that was added, for instance, if this is a particular kind of linked list. So you would end up saying something like, let L be a set of all elements stored in the list. You end up with some invariants, some things that you know to be true by the time that you start this. Again, we'll go in way more detail about this. You don't need to memorize this process by now. This is just kind of an overview of software engineering concepts and what they are. So these are annotations. These are added to your code by some programmer, some software analyst. You write them directly into the program code, and they tell you aspects of the logic of what must be true at this point in the code. Some examples of this, we've talked about some of these if you've taken prior classes from me. Preconditions and postconditions tell you what must be true in order to run this code. So what are necessary properties of the input? So a precondition to a particular method might be the list is instantiated and has size at least 1. Otherwise, this program may crash. So all preconditions must be met before moving into a particular part of the code. Postconditions tell you that if the preconditions were met and the code is run, then the postconditions will be met. Something that tells you if the list was size n and we ran this add function, now the list is of size n plus 1. So we get a lot of logic in there, if then from discrete as well. In general, invariants will just tell you properties that have to hold at every point that the user has control. Think of it like a list will always have some number of elements in it. Maybe you, in the middle of a method, make that list empty, but by the time that method finishes, the list has something back in it. So the invariants can be violated in the middle of a function, but by the time a function is finished or the user has control, all the invariants must be met again. So at some point you may be asked to come up with a list of invariants for a particular piece of code in industry, and that's what that means. What must be true at every control point in your code. You end up with something like a verification condition. So you can turn this into some predicate logic, and then you can reason about that predicate logic to verify the truth of that predicate logic. I hope you enjoyed this screen.
I took it to
If you're taking it now, this is the future fun of the applications of how math will be relevant to computer science. It all comes back. These fields are extremely tied together. Unfortunately, the way math is taught most frequently is very formulaic and proof-based. If this annoys you and is not the way you learn, welcome aboard. It's the exact same for me. It's something I struggled with as an undergraduate and graduate student, trying to learn how to read and understand math. If you take additional classes from me, I will always do my best, wherever there is math, to break that down into logic and English, drawing diagrams, creating things, ways that you can visualize that information linked to other information that you know, because it's really important for you to know it. I see and hear many students running, screaming for math, and to whatever extent that you can engage with it, please do. It is extremely important to the future, your future in this field. It's just not always presented in a way that is the best for your learning. You should advocate for your learning, find ways to help you to learn this material. Come talk to me if this is something that ever goes on for you in math classes. I anticipate that's about 95% of the class. And it's something that I really enjoy talking about and helping people to discover. I know quite a few resources for helping you through some of the math classes that you'll end up taking. The more you can take out of those classes, the easier future classes are going to be, the more you're going to understand. I hate to be that person, an advertisement for a brand to grab life by the horns, grab your academics by the horns, and engage with it to whatever extent you can. Sounds like a horrible one, but it's super important. Getting back to this, we can derive formulas from our code based on the code and the annotations in the code. Then we can turn this into verification conditions. And if those verification conditions are always valid from discrete, or if those conditions always hold, then the code ends up being correct with respect to the property that we're trying to prove, we're trying to show. Which means that no matter what the input variables are, even if there are an infinite number of potential input variables, you have shown that that property holds. If the verification condition does not hold, or you find some issue with the proof, then there's an issue with the code. The question is just, where is the issue with the code if the math tells you that this isn't always true when it should always be true? There is software out there that can verify for you. It will do some of the brunt of the hard work. I would argue that you should never use technology that you don't understand the inner workings of, at least in a job setting. I won't state that I understand all of the inner workings of ChatGPT, but I occasionally use it. You can leave for really funny things like writing the meanest possible email to someone and then never sending it. It's very fun if you can get ChatGPT to be mean. Really funny.
Have you seen that?
It creates burns that I could just wish that I could come up with and say. I sent one to my TA, actually the hunter last quarter as a joke. Just like, ouch, I don't know if I can ever recover from that. It was great. I'll share it eventually. So as input to the verifier, you take annotations and you take the program. So a list of annotations, you feed those as input to the verifier. the verifier converts this into mathematical formulas, feeds those formulas to a mathematical theorem prover, which asserts either that those theorems are true or false. If they are true, then the code is correct. If they are false, there is at least one issue with the code. Even using this kind of software is difficult to do because you have to have perfect annotations and a program and know exactly how to mathematically formulate your question. Has anyone ever heard of Prolog, the language? That's a very discrete type of programming language. If anyone's curious, look it up over the weekend. It's a logical language. Instead of making statements like you're used to in Java, you will actually make assertions, truths. And then you can query the database basically to say, is this statement true? And the language goes through and derives as many truths as it can in a formulaic fashion from the statements that you've given it and determines, yes, that statement is true, or no, that statement is not true. So a logical language that is very different from the kinds of language you use. We cannot verify everything, but on the other hand, there are some things that are very important to be verified. Think of something like the Windows operating system. Windows 10, about 50 million lines of source. Think of just how much math is necessary to verify that Microsoft Windows does what it's supposed to, that it doesn't leak private data, that it's et cetera, et cetera. There's a lot of work that goes into this, and it's always ongoing. There's a reason why we have security vulnerabilities, security patches all the time, is that a lot of this is being done behind the scenes. When issues are found, vulnerabilities are discovered that need to be patched. Yeah.
I mean, wouldn't this also include the whole, what was it, the cloud space incident where somebody completely just deleted a whole chunk thinking it wasn't necessary, but it crashed the entire system?
Absolutely, absolutely.
Oh, boy.
There's a lot going on behind the scenes. The more you know about how it all works, the more informed decisions that you'll be able to make as you're put in those leadership positions. And you can at least advocate for whenever someone comes up with a really dumb idea, you can vocalize, that's a really dumb idea. And you'll go formulaically, nothing works better than proved. That idea is dumb, let me express it as logic. And you actually write out the mathematical proof that their language is ridiculous. And they look at you and they never want to talk to you again. Story about. To summarize, just this entire slideshow has been kind of an overview of everything we're going to talk about in the class. We're going to dive into all of these in a lot bigger detail, but engineering, boils down to several issues. We need to be able to write specifications. We need to be able to figure out what is it that exactly we need to do in order to accomplish the goals that our client has given us. We need to be able to design the solution. We don't want to just start programming the solution. We're going to spend a significant amount of time figuring out how are we going to do it. Once that process is done, we will start doing it, implement exactly what the specification and design tells us we need to do. Once we have done it, we need to verify and validate that what we have done is what we said we were going to do. Questions about the process as a whole in general? Those are the big important steps. Specification, design, programming, and validation. There are some important disclaimers about how this class is going to be run. I am pretty good at well-defined technical problems. If you come to me with a well-defined problem, I'm usually able to help you with it. If you do not have a well-defined or non-technical problem, I may not be as good at solving it. So as you're doing this project, you're going to be off on some tangent that is not directly step by step a predefined lab that has a predefined set of kind of checkpoints. So if you bring me a project that you've been working on for hours and hours and is spread across multiple files that multiple people have been working on, and you say, what's wrong? That is a huge, ill-defined problem. I don't know where to start, and it's non-technical. I don't know where to start. I can't really help with that. So that kind of problem is something that I can help with if it's a pre-described lab that I've solved myself, and I have quarters worth of experience troubleshooting students' problems with, so I know all of the likely fail points. This project is not like that at all. You're gonna be working with different technologies than I have used historically. You're gonna be working with different code. You're gonna be working in groups trying to understand each other's code. I'm gonna be taking, for the most part, a managerial role, which means that your first point of failure is going to be the rest of your group. Each of you are going to be much more involved in the day-to-day part of creating your project. That is not to say don't come to me with those problems. Please do. But come to me with the expectation that I'm probably going to be more clueless than you are, or it's going to take me a lot longer or a lot more time than I have to be able to fully dissect. Here's what you have, here's what's wrong, here's what you need to do. I'm more than willing to give that the best shot that I can, but it's not like most classes you've taken in the past. So talk to your group, work through it together to the best extent that you can. If you're all stumped, I may be able to give you some kind of push. It may not solve the whole problem, but it may point you toward a technology. This reminds me of some issue that I've had when I did this. This kind of search is what helped me find the answer. Because of that, procrastination is also not going to play well in the class, because you come to me with this issue the day before a sprint is due. There's no way that I'm going to be able to find a solution, portray a solution. You're going to have time to implement a solution, test that solution, discover what's wrong with that solution, go back and try again. All right. Let's start talking about software engineering processes. So we're going to start by talking about the most basic process or way to create software that has been done historically and is an important concept in modern methods. So this is not all that is done, but it's important to understand because it is a part of the modern process. Has anyone heard of the waterfall model before? All right, let's learn about it. So we're going to break software engineering down into a sequence of phases. And you can imagine this as kind of a timeline from left to right, as well as the steps from top to bottom. So we kind of have a two-dimensional chart here. So we're going to start by gathering the requirements. And note that gathering the requirements is often a process that takes a while. Once we have enough requirements, we can start the specification. Once we are done with the specification, we can start the design, then we can go into implementation, go into integration, and eventually we have a product that we can ship. We're going to talk about each one of these phases in much more detail. Note that testing is not a separate step. It is something that is done from start to finish. So there's no real timeline to start that testing. Start it as soon as you can. And you'll be testing all the way until you have a final product. So the requirements phase. Just like before, when I drew this on the board yesterday, we're going to have this concept of the finished product is a hexagon, a filled hexagon. So visually, you can think of gathering the requirements as kind of figuring out, you first figure out what are the boundaries? What is part of the product? What is part of the scope of the product and what is not? So you're thinking about what shape are we actually drawing here? So there's no way that this is going to be some kind of dodecagon. Probably also not a triangle. We've already gathered enough resource to know that this isn't gonna be some kind of triangle. This is gonna be a larger shape than that, but probably not something that's significantly more than 5, 6, 7, 8 sides. We also start to get some ideas of, okay, there are some requirements in here. I get an understanding of how some pieces of this are going to fit together. But note that it's not all encompassing. This is done by talking to the client. You should think of it as a raw list of features. What does our program need to be able to do? This is not technical. You're not figuring out how to do these yet. It's just what is part of this project and what is outside of the scope of this project. This is not something you do in your head. This is something that you have documentation for. To do this, you need to communicate with non-technical people. You need to talk to eventual users of your product to figure out the requirements. You need to talk to any clients who's actually going to be paying you for this, to potential customers. Who's going to be using this? What are they going to be using it for? How do they want to use it? Note that you have nothing to give them at this point, so you can't do any user testing. You can't sit them down and say, use my product. What do you like and not like about it? This has to be all abstract. You're talking just about what is part of this and what is not. What would you like to see here? And then the technical you is going to come up with this list of features. What is part of this and what is not? You want to make sure you don't build the wrong thing. You do all of this as much as possible before you start planning how you're going to actually implement it. Because as you've seen, you add one new feature to something and it may completely change how it looks in code. And it makes me wish that I remembered something from yesterday. I'm gonna see if I can find it maybe by the end of class. But it was again from r/programmer humor, great subreddit for anyone who wants to go find things to laugh at. But it was an image of a perfect highway intersection. It was code with 1,000 features. And then the second image was this nasty map of highway interchanges, massively overcomplicated. It said same code with 1,001 features. Add one feature and the entirety of this code that made sense needs to be completely redesigned sometimes. And the resulting work is gross. The more requirements you gather in advance, the easier the planning is going to be. The idea is you don't want to come back to this gathering requirements because that's going to involve an entire redesign of this code. How realistic is that? Sounds like a lot of wishful thinking, huh? Is the client going to change what they think they want? Once you have a designed prototype for something and hand it to the client, are they going to go, that's not what I said. I wanted this, not that. Oh, I see how it works now. Could we include this? All of those are non-technical asks that you may want to decide that you want to be able to handle. And we'll talk about this later when we talk about some of the issues with the waterfall model by itself. But in terms of just the waterfall model, we're going through these steps and we're going through them once. So this is the gather requirements phase. Next, we move into specification. So the goal of specification is to take the prior design and turn this into the idea of that. So we're going to plan and say, all right, here are the boundaries, here are some of the components. I think what we want to design is this. Great. Again, this is a written document. It's going to describe exactly what the system does in as much technical detail as you can. Every circumstance for all inputs in every possible state. The idea here is to be incredibly thorough. about exactly what does this do. It doesn't say how it does it. The idea is to define success or failure. This specification is gonna be what we come back to decide whether we've created the appropriate thing. Does this program do everything that the specification tells us? If the specification is vague, the program will pass the specification and not match the client's needs. So we need to make sure the specification is as good as possible, as detailed as possible. Think about every edge case, every error case that you possibly can, and write down what the program should do in all of those cases. So we have a written document. It's not just the requirements, it's every possible state the program could be in. Great. Now we have a document that tells us what we need to make. Now the question is, how are we going to make it? So we need to figure out the actual system architecture of this solution. So now we're actually going to break this hexagon down into some components. Each of those components are a subsystem of this overall system. Think of this as the system architecture. We now define what the modules of the system are. So for the scope of this project, since you have multiple people on your team, each person can be responsible for a different module. This also tells us what the interfaces are, kind of the boundary points where one module ends and another module begins. Who's responsible for what, as well as what parts of the system are responsible for what. This is part of the design. This is where your technical expertise is going to come into play. This is how the system works. We're not defining what it does anymore. This is how we're going to do the what. By the end of this process, we can break apart these modules into individual components. And now you can assign person 1 to this module, person 2 to this module, person 3 to this module. These are independently developable subcomponents of this system. That is not to say that there is no necessary communication between these subcomponents, but they're at least components that you can build and test independently. Not fully test, we call this integration testing, when we have different modules communicating with each other and testing each other's functionality. But you can see that we end up being able to draw any number of lines between this and separate different modules and components of modules so that we can create levels of subsystems. Questions about anything we've talked about so far? Yeah,
So, for each piece of this, each individual should know exactly what he needs to do and his piece of work, how it contributes to the whole system.
yes,
Should he know about the other pieces also?
yes. Less so the exact technical process behind it, but you should be able to point to this piece is constructed from this part of the specification. These parts of the specification are necessary to build this part. Everyone should be aware of what everyone else is doing because the person who designs this may need to write some code that communicates with this. So very early on, this person can ask this person, how are you doing this so that I can interface with what you are expecting? Because that's also part of the design of this component, but it's not something that you can test by itself. So there is significant communication between all of this. This is just the man hours of the person who's responsible for this, but yes, this person should have an understanding of everything that's happening in the system and how it affects their individual component, so that they can produce the best component that they can, so less work has to be done in the future, when you try to put it all back together. So this is still all in theory, right? We're still designing this. We haven't actually written a single line of code yet. This is all planning ahead of time. So implementation, now rather than the idea of this hexagon, which was purple, now the actual components of this as we write the code are going to be in red. So now we have actual code for each of these components. So we code up the design. If you have a solid design for the exact technical specifications and exactly what technology we're going to need, this should be a relatively easy process, at least easier than the specification and easier than the design. If you have some document to work off of, you're just doing exactly what someone else told you to do. So we do need that plan, order in which things are going to be done. Usually you have some kind of priority list. These are very important to the functionality of the overall product. These are less important to the functionality of the overall product, but it's also for testing. You want to be able to test a minimal working version of the product as early as possible. So that means what aspect of this needs to be written so that we can test this component? What needs to be written so that we can test this component? You don't want to write the entire module and then start testing it for the first time. So make sure that you are testing each module as you're developing it, as well as when it's finished. Step 5, integration. Now that each of these components were written individually by individual people who all knew what each other was doing, but didn't necessarily have their hand in exactly the line-by-line writing of it, now the goal is to put all of the pieces back together. Because this is not a hexagon, it's a bunch of triangles. So this is a huge testing at this point, because you need to make sure that the system works all together in the way that the specifications define. So in addition to all of the testing that showed that the individual modules work, now we need some testing to ensure that this system, once we put it all together, matches the exact specifications. And I did this on purpose. There's a little bit of purple leaking through at the side here. The reason that that is there is that regardless of how much work you put into something, there's always going to be either not enough time to fully implement all of the features. There are going to be some bugs, something doesn't quite work as well as you can. The goal is to minimize the size of this purple. You want to produce as much actual code that maps to the specifications as possible. That's usually completely infeasible. You just want to minimize that. So now you need to test the entire system, discover where is there purple if there isn't red. Then you can go back to it and make sure you fill in those holes. Finally, you end up with the product. There it is. In the waterfall model, you ship it and it's done and it's perfect and you throw yourself a party. What you really have is the release of No Man's Sky. Actually, you need to start maintenance on it and make sure that any issues that your users discover with it continue to be addressed. So this is the waterfall model. This was a significant model in the 80s, early 90s. It's still an important part of what we do, but obviously engineering has developed past this point. So we are going to come back to this on Monday, and we're going to discuss some pros and cons to this, as well as build on it to eventually arrive at agile development, which is what we will be implementing in our development in this class. Have a great weekend. Look out for that assignment. I don't exactly know what it's going to look like. I'm going to talk about it, and we're going to figure out exactly the information for you.
Yes, they must be. Absolutely, that's all. I am.